In this video, we're going to take a look at different important discrete time signals. The first signal that we consider is the unit impulse function, denoted delta of n, and it's defined to be equal to 1 for n equal to 0, otherwise it's defined to be equal to 0. This is an illustration of the unit impulse function. We can also shift the unit impulse function, so in this case we're shifting the location of the impulse to time n is equal to m. Note that the definition for the unit impulse function is a well-defined sequence. And so this is in stark contrast to the continuous time case, where we had to define the delta function, or the impulse function, through the integral. If we integrate over all of time, delta of t dt, this would give us 1. The next signal that we'll consider is the unit step function, denoted u of n, which is defined to be equal to 1 for n positive, otherwise it's defined to be equal to 0. And this is a graphical illustration of the unit step function. It's very similar to what we have in the continuous time case, and it's mainly used as a switching device. In particular, it's used to build up more complex types of signals, or effectively used to denote when a particular signal is going to start in time. If we multiply a signal with u of n, then that means we're starting our signal at time n equal to 0, but we can also start our signal at any arbitrary time by simply shifting our unit step function. The unit impulse function and the step functions are related by the following relationships. In particular, the impulse function is given by u of n minus u of n minus 1. This is referred to as the first difference of our unit step function. This is similar to the continuous time case, where the delta function was given by the first derivative of the unit step function. We also have that the unit step function is given by a running sum from n equal to minus or k equal to minus infinity up until time n of the impulse function. And this is similar in the continuous time case, where u of t is given by the integral from minus infinity to t of delta of tau d tau. The next signal that we'll consider is an exponential signal. X of n is equal to gamma to n, where in general gamma is a complex number. We can write gamma in polar form, so it's written as rho e to the j theta. If we take a look at the complex plane, our point gamma could lie over here. Rho denotes the distance that the point makes from the origin, whereas theta denotes the angle that the point makes relative to the x-axis taken counterclockwise. So our exponential signal, x of n, which is equal to gamma to the n, is simply going to be rho to the n e to the j n theta. So we have sinusoidal variations with an envelope. If rho is less than 1, then the oscillations arising from our sinusoidal variations will have a damped amplitude. If rho is greater than 1, the oscillations will have a growing amplitude. And if rho is equal to 1, the oscillations will have a constant amplitude. The frequency of the oscillations are going to be set by our angle theta. The more theta approaches pi, we're actually going to get faster and faster variations. With regards to the amplitude, whether rho is less than 1, greater than 1, or equal to 1 to have a damped amplitude, growing amplitude, or constant amplitude, these three cases correspond to the value of gamma lying either inside, outside, or on a circle of unit radius, or everything relative to the unit circle. Here are some examples of exponential signals. 0.8 to the power of n. In this case, the magnitude of gamma is less than 1, so it's inside the unit circle. We have a decaying exponential. We have 0.5 to the power of n. In this case, again, the magnitude of gamma is less than 1, so we're inside the unit circle. We have a decaying exponential. But note that here, the magnitude of gamma is less than the magnitude of gamma here. In fact, we're closer to the origin in this case, and so the rate of exponential decay is even faster. In this case, we have 1.1 to the power n, so the magnitude of gamma is greater than 1. It's outside the unit circle. We have an exponentially growing envelope. Finally, in this case, we have minus 0.8 to the power n. The magnitude of gamma is 0.8, which is inside the unit circle, so we have to have an exponentially decaying envelope. However, due to the minus sign, our signal is actually going to alternate between positive and negative values as shown over here. In fact, we can write minus 0.8 to the power of n as simply being 0.8 times e to the j pi to the power of n. So in this case, theta, which is the angle that our value of gamma makes relative to the x-axis, is equal to pi. And so we have fast variations because we're toggling effectively from a positive to a negative value in consecutive time slots. In the continuous time case, we define an exponential signal as x of t is equal to e to the lambda t, where lambda is in general a complex number. In the discrete time, we can also write an exponential signal x of n as being equal to e to the lambda n, where in this case we simply let gamma equal to e to the lambda. Oftentimes, however, for discrete time signals and systems, it is preferable to make use of an exponential signal denoted as gamma to the n rather than e to the lambda n. But let's consider the mapping between gamma equal to e to the lambda a little bit further. In the continuous time case, the value of lambda actually defined the type of exponential signal that we had. In particular, if lambda is purely real, we would either have an exponential increasing signal, an exponentially decreasing signal, or a constant amplitude signal. If lambda was purely complex or purely imaginary, then we would simply have a sinusoidal signal. And if lambda was in general a complex number, then we would have a sinusoidal variation with an exponentially increasing envelope, an exponentially decreasing envelope, or a constant envelope depending on the value of the real part of lambda. So in particular, if the real part of lambda was positive, then we know that we would have an exponentially increasing signal. If the real part of lambda was negative, we would have an exponentially decreasing signal. And again, if real part of lambda is equal to 0, then we would have a constant amplitude signal. So lambda equal to 0, the real part of lambda equal to 0 denotes this imaginary axis. If we put lambda equal to 0 in the mapping gamma equal to e to the lambda, then this imaginary axis actually winds up mapping to the point gamma equal to 1. So it maps onto the unit circle. So, in the continuous time case, if we have real part of lambda being positive, so we're here in the right half plane, this would correspond to values of gamma that are outside of the unit circle. So if real part of lambda is positive, corresponds to exponentially increasing signals in the continuous time case, then in the discrete time case, gamma greater than 1 is going to correspond to exponential signals that have an increasing envelope. For the real part of lambda being negative, so here in the left half plane, this is going to correspond to values of gamma that lie inside the unit circle. So for real part of lambda being negative, where we have an exponentially decreasing signal, well, in the discrete time case, gamma has to be inside the unit circle and we'll have an exponentially decreasing signal. And finally, if we lie on the imaginary axis, so the real part of lambda is equal to 0, and so we have lambda being purely imaginary, this is going to map onto the unit circle. So in this case, gamma is equal to 1, the magnitude of gamma is equal to 1, but in this case, we're going to have a purely sinusoidal variation with a constant envelope. If you have any questions, please send me an email.